Good afternoon, class. We are looking at exam 3 review that covers section 3.5 to 4.2, 3.5, the chain rule, implicit differentiation related rates, 3.7, derivatives of the log functions, 3.8, differentials, 4.1, maximum and minimum values, 4.2, how derivatives affect the shape of a graph. First, we have differentiation formulas from the basics to sinusoidal functions. We have, of course, the definition, product rule, quotient rule, chain rule, exponential functions, logarithmic functions. Then delta y, which is f of x plus delta x minus f of x. The change in y along the curve versus dy, which is f prime of x dx, and it will be the change along the tangent line. So dy and delta y are not the same, but delta y can be approximated by dy, and a point with coordinates a and f of a instead of x and f of x, we can use the point slope to represent linearization, which in essence is simply finding the tangent line. Logarithmic properties, if we understand this arrow, which means b to the power of y is x, we can go from logarithmic format to exponential format and vice versa. B must be positive, can't be 1. So we need to be very comfortable with logarithmic properties. It gives rise to the following properties. Log 1 with any base is 0. Log b base b is 1 when the argument and the base are the same, the answer is 1. These two, log b to the power of x of base b is x, b to the power of log x base b is x, refer to the fact that logs and exponential functions are inverse functions. Product rule, quotient rule, power rule. Log of xy is log x plus log y, same base b. Log of x over y is log x minus log y, same base b. Log of x to the power of n is n log x when they have the same base. Now, when we use log and not the base, that means the base is 10. It makes it a common log. So we can write the properties for a common log. When we use ln instead of log, the base is e, and these are the properties. And this graph represents y equals e to the power of x, y equals ln x, and they are inverse functions, therefore symmetric with respect to the line y equals x. Here's the change of base formula. So for the logs, ln x, we know how to differentiate it. We just flip it over. In this case, flip it over times g prime of x. When the base is something else, we need this by the chain rule, 1 over ln b. So this is the synopsis of what we need to move on. Let's start looking at some examples. 2x plus y to the power of 4 equals x minus 2y, and we want to differentiate it using implicit differentiation. Dy dx or y prime makes no difference in this case. So we are going to use the extended power rule. We take the 4, we put it in front, 2x plus y cubed, and then times the derivative of the inside, which is 2 plus. Now, the derivative of y is dy dx or y prime. And on the right side, x gives us 1 minus 2, y gives us y prime or dy dx. We are done with calculus. We are going to solve for y prime. To do so, you can distribute, but here's an easy way. Just multiply 2 by 4, you get 8. And then this expression times y prime. So on the left side, if I multiply 2 by this expression, this becomes 8. And if I multiply y prime by this expression, I don't have to make any changes. I just write this and then y prime. Now we are solving for y prime, which means I'm going to move this to the left and make it plus 2y prime. And I'm going to make this to move it to the right and make it minus 8 times 2x plus y quantity cubed. So we move things around. We're going to solve for y prime, so we are going to factor the y prime out. Of course, I can take 2y prime out. However, on the right side, there's no common factor of 2. I just take the y prime out. So when I take the y prime out, this gives me 4 times 2x plus y cubed. This gives me 2. And all you have to do, put the brackets as the denominator for the right side and call it y prime or dy dx. Makes no difference. We are going to continue differentiating using implicit differentiation. Sine y plus 2x cubed y squared equals 6. First and foremost, sine. Remember, with the sinusoidal function, you just pause, and that means the main function, the shell function, the outer function is sine, the derivative is cosine. So cosine of the same argument, cosine y, and remember, y is g of x. Y is the same as g of x. Let me just write this here. So y in essence is the same as g of x. So times g prime of x, or times y prime, or times dy dx. So cosine y times dy dx. I'm going to put a raised dot here. F times g. We're going to use the product rule on that. 2x cubed gives me 6x squared times y squared. This is f prime, now g, plus, now y squared. The derivative of g of x to the power of n is n g of x to the power of n minus 1 g prime of x, and we're going to replace the g of x with y. It works the same way. N y to the power of n minus 1 y prime or dy dx. So this will be 2y y prime or dy dx, and then times f 2x cubed. The right side is a number, becomes 0. So we have f prime g plus g prime f. And we are practically done. We just solve for y prime or dy dx. And to do that, first 2y and 2x cubed would get multiplied 4x cubed y. Then this is the one that we are going to move to the right, becomes negative. So what is left? On the left side, we take out the dy dx. So this gives us cosine y, this gives us 4x cubed y, and this moves, becomes negative on the other side. So these two, we just took the common factor of dy dx out, divide by the parentheses, and we are done. Find an equation of a tangent line. 2x squared plus 2xy minus y squared plus x equals 2 at a specific point. We need two things. We need a point x comma y is given. We also need a slope when we want to find the equation of any line. So for the tangent line, how do we find the slope? We find y prime or dy dx. We are going to do it implicitly. Therefore, x squared gives us 2x. I put a raised dot between 2x and y, and I call it f times g. So I'm using the product rule. Two x gives me 2 times y, plus y gives me y prime or dy dx times 2x. So right away, let me write this at top of it. So I have f prime g plus g prime f. Now minus y squared minus 2y prime or dy dx plus x gives me 1, any number gives me 0. Now, we can plug in right here, and if we plug in x and y, we get this slope. That's evaluation of this slope. However, let's solve for y prime by moving things around as follows. So let's move the 2x to the right. Becomes negative 2x. Let's move 2y to the right. Becomes minus 2y. Let's move positive 1 to the right. Becomes negative 1. And on the left side, I can take the 2y prime out, but on the right side, I don't have a common factor of 2. I'm going to just take the y prime out, which gives me 2x minus 2y. I can divide by the parentheses, and that's y prime or dy dx. To find m, we have to plug in. So plug in what? The pair. So I'm going to write with this type of notation, y prime evaluated at 1, 2 will give us minus 2 times 1 minus 2 times 2 minus 1 over 2 times 1 minus 2 times 2. And I hope you see we have minus 7 over minus 2, which is 7 halves. So we use y minus y1 equals m times x minus x of 1. So y minus 2 equals 7 halves x minus 1. So the right side is 7 halves x minus 7 halves. If I move the negative 2 and make it positive 2 or 4 halves, then we have y equals 7 halves x minus 3 halves as the equation of a tangent line. By the way, the pair belongs to the graph of the original curve as well as the tangent line. So if you plug in 1, it must give you 2, and it does, which indicates this process was done right. Doesn't tell us anything about y prime, whether we did it right or wrong. Okay, so it's important to know it doesn't give us information regarding that. Okay. We want to find dy dt for this equation x e to the power of y plus 4x equals y cubed, where dx dt is 2, x is -1, y is 0. The moment you see dy dt or dx dt, it tells you t is the independent variable, which means the derivative of x is dx dt, but not 1. The derivative of y is dy dt. So you want to avoid writing y prime, okay? And so to differentiate this, I'm going to put a raised dot here again. F times g, and we are going to use the product from f prime. That means dx dt times g. That means e to the power of y. So the derivative of x is dx dt times e to the power of y, plus the derivative of e to the power of y is itself times y prime or dy dt times f, which is x, and let me write this as f prime g plus g prime f. And then we have 4x, 4 dx dt, y cubed 3y squared, dy dt. We are done with differentiation and calculus. We are going to evaluate by just plugging in. That's the fastest way, although we can solve for dy dt and plug in afterwards. We don't have to. So just plug in. Plug in. So what happens when we plug in? Dx dt is 2 e to the power of y or e to the power of 0 plus e to the power of 0 dy dt is missing. X is -1, 4 times dx dt, which is 2. The right side 3 times y, which is 0 squared dy dt. And so we have, this is 0. This is 1. This is 1. So we have 2 minus dy dt plus 8 equals 0. And I hope you realize if I move this to the right, makes dy dt equals 2 plus 8 or 10. Again, the key here to pay attention to the independent variable, namely t. When I differentiate f of x equals 2x times ln of 3x squared, I can decompose ln of 3x squared, but it doesn't really help. Instead, I put a raised dot here. If you call this f, this is g, so f prime 2 times g ln of 3x squared plus g prime. We want to differentiate this. Remember, with the ln, flip it over 1 over 3x squared, and then times g prime. So 1 over 3x squared, g prime is 6x, and then times f 2x. By the way, again, I could have decomposed this. It would make it more difficult, and I hope you realize. So basically, this doesn't change, and I hope you see this simplifies to simply 4, because it's 12x squared over 3x squared. And we're done. We are going to continue with differentiating a natural log, and if we were to do it just the way it is, we have to flip this over and then we use a quotient rule. We don't want to do that because there's an easier way, and that would be to use logarithmic properties to decompose this first. Anybody knows how we decompose this? Logarithmic properties. We use the quotient rule, ln of the top minus ln of the bottom. If you left it as that, it's okay, but ln of 5x is ln 5 plus ln x. And ln 5 is a number, which means this derivative is 0. So ln x gives you 1 over x minus, flip this over, 1 over x squared plus 5 by the chain rule times the derivative of that, which is 2x. We're done with calculus. To combine the two, we take a common denominator of x times x squared plus 5. This becomes 1 times x squared plus 5 minus 2x times x in the numerator, which becomes x squared plus 5 minus 2x squared. Now we can combine x squared and minus 2x squared into minus x squared, and that's the final answer. All right. We're going to continue differentiating. We're dealing with the log. The first step is to decompose it, and we can use the power rule, put the 4 in front. Now to differentiate this, 4 remains unchanged. We flip this over. By the chain rule, we need the derivative of that times negative 3x squared. Because the base is not e, we are not dealing with natural log, then we have to divide 1 by natural log of the base. Since the base is missing, that means common log. The base is 10, so 1 over ln 10. And all you have to do, put these two together, 4 times minus 3x squared, negative 12x squared is the numerator. As far as the denominator is concerned, we keep it in this format. We're not going to put this after ln 10 because one may think it's part of the argument of natural log. So we keep it intact in this format. We are asked to come up with dy, and to come up with dy, first we differentiate. We find f prime of x or dy dx, which requires the quotient rule. And so dy dx or f prime is the derivative of the top, which is 2x times the bottom, which is x minus 8. We are using the quotient rule, everybody. Minus the derivative of the bottom is 1 times the top, which is x squared, 1 times x squared. And you just write the bottom in a parenthesis and square it, and we are done with f prime of x, which means the calculus part. And we are going to simplify the numerator by combining them in the following manner. We have 2x squared minus 16x minus x squared, and these two combine into x squared. And that's f prime or dy dx. Dy is the same thing, everybody, just times dx. You want to evaluate dy and delta y. When x is 4, dx or delta x is 0.2. So we are going to plug in. Now, of course, this is 16. This is 64. So 16 minus 64. This is negative 4 squared is 16. minus 48 divided by 16 is negative 3 times 0.2 is negative 0.6. Delta y is simply f of x plus delta x minus f of x. So f of 4.2 minus f of 4. So plug in 4.2, 4.2 squared over 4.2 minus 8, and plug in 4. Just do the math. You can use even a calculator and end up with negative 0.6421. Notice the two values are extremely close. Use differentials to approximate cube root of 63.5. When that happens, we need two things, class. Number one, we need a function that gives us the same action. What function would give us the same action? Cube root of 63.5, so cube root of x. Cube root of x. Then we need a number closest to 63.5 so that we can find the cube root easily without any calculators. What number would that be? $64, because the cube root of 64, we should know it's equal to 4. So we want to use 64 as x, therefore dx is 63.5 minus 64, making it negative 0.5, meaning we know the cube root of 64 is 4. The cube root of 63.5 is less than that. This is the idea that is put in here. For example, if I said what is cube root of 65, I want to discuss the dx. dx would be 65 minus 64, which is positive 1, meaning we may not know what this is, but it has to be larger than cube root of 64, which is 4. That's the way it works. So with that being the case, f of x plus delta x is f of x plus dy. So this is the approximation that we are going to use. So f of x is given, dy is missing. To find the dy, first we have to differentiate this. So we are going to write this as x to the power of 1/3. Then we're going to write this as 1/3 x to the power of 1/3 minus 1, or negative 2/3. That's the derivative. Or we can take this down, make it x to the power of positive 2/3, or 1 over 3 times, this is the 3, cube root of x quantity squared. So what is dy? Exactly the same thing, times dx. So you can say times dx, or you can put the dx at top. It makes no difference. So this is f of x, this is dy. We want the cube root of 63.5, which means we want f of 63.5, where x is 64 and dx is negative 0.5. So plug it in. Plug it in. We are going to evaluate this expression. So this is 4. This is 4 squared is 16 times 3 is 48. So this is negative 0.5 or negative 1/2 over 48. So again, this is 4. This is 4 squared 16 times 3 is 48. Why am I changing negative 0.5 to negative 1/2? Because I want to write this as a fraction. So this is 4, and this is, if you multiply 2 by 48, you get 96, minus 1 over 96, which makes it 3 and 95 over 96. And here's the decimal representation. Why am I using this? Because this is the exact answer. Why am I using the decimal representation? I want to use a calculator to evaluate this, and a calculator gives me this number. Notice within 4 decimals, 1, 2, 3, 4, they are the same. In fact, if I stop here, I have to change it to 6 because this number is 5, the same thing here. So that's a very good approximation, everybody. I want to remind you of the second method, or linearization, which simply put, you find the tangent line at x equals 64. At x equals 64. So if I plug in 64, I get 4. My pair x comma y is 64 comma 4. So if I put 64 into the original function, I get the pair 64 comma 4. If I put it into f prime, I get this slope. And as you know, this is cube root of 64. 4 squared is 16 times 3 is 48. So 1 over 48. This is how we get the pairs. Okay, everybody? So y minus 4, y minus y1, 4 equals m 1 over 48, x minus x of 1 is 64. And I'm going to leave it for you to show that this is, when you move the negative 4, this is the answer. This is L of x. So what do you have to do? You have to plug in 63.5. And I highly recommend you do that with fractions, because it gives you exactly this. And if it doesn't, somewhere we've made a mistake. So that's the exact answer. Differentials or linearization must give you exactly the same answer, everybody. We want to find the absolute max and mean values of f on the given interval. F of x is x squared minus 1 quantity cubed, and the interval is negative 1 to 2. First and foremost, notice this is a polynomial. What is the degree of the polynomial? 2 times 3. Every polynomial is continuous from negative to positive infinity, therefore it's continuous in the given interval. So that's the first thing we should notice. Then the methodology. Number 1, find f prime of x. So 3 times the same thing squared times the derivative of the inside, which is 2x. 3 times the same thing squared times 2x. And now we should set this equal to 0. So I can simplify it. I don't have to. You notice it just, this one gives you 0. This one gives you x squared equals 1. And x is plus minus 1. There are 3 answers, everybody. Okay. There are 3 answers. I want you to notice that there are 3 answers. And therefore, you have to see which one is in the interval of interest. Number one, -1 is one of the endpoints that works. +1 is in between, that works. 0 is in between, that works. We have to evaluate the original function at a, which is -1, at b, which is +2, and then the other 2 points, 0 and 1. I'm going to put them in order. That those are the critical points. So we have to do this, everybody. Now I'll give you the answers. So basically what you need to do is to plug in these numbers into the original function. For example, if I plug in -1, squared becomes +1. 1 minus 1 is 0, so this is 0. If I plug in 1, the same thing. If I plug in 0, this goes away, -1 cubed, which is -1. If I plug in 2, 2 squared, 4 minus 1, 3 cubed, 27. Largest number is 27. So absolute max is equal to 27 at this pair. The smallest number, -1. Absolute mean is -1 at this pair. So this is how you write it. Now, as far as writing is concerned, again, you want to write it in a manner that they want you to write it in order for you to receive full credit. They may ask you for just the max, which is this number. They may ask you for the pair. So you want to follow that accordingly. Okay, everybody? All right. A small rock is dropped into a lake. Circular ripples spread over the surface with the radius of each circle increasing at the rate of 3/2 feet per second. Find the rate at which the area of a circle is changing when the radius is 4 feet. So it's a word problem. We want to write down the given information. And I'm going to remind you that when you deal with the circle, the area is pi r squared, right? These 2 times r, here's the radius. These 2 times r. And the circumference, when we go around it, 2 pi r. Because we are dealing with the area, we just want this formula. We don't need the other two. Okay? But I wanted to remind you of that. So a equals pi r squared. What is given? It says the radius is increasing at this rate. Rate refers to differentiation. dr dt is 3/2 feet per second. What do we want? dA dt. At what point? When r is 4. So this is the translation of the question, everybody. We are going to differentiate this with respect to time, t. So dA dt is pi, because pi is a number, doesn't change. Just r squared, everybody. 2r dr dt. 2r dr dt. Let me. Sure. So r squared is 2r dr dt. And so 2 pi r dr dt, plug in. R is 4, dr dt is 3/2. These two cancels out, these two, we have 12 pi square feet per second, and this is an approximation. By the way, you always want to stick with the exact answer. As far as the units of the numerator, the change in the area, square feet, over the change in time. So it should work, and it does work always. A spherical balloon is deflating, losing 8 cubic centimeters of air per minute. At the moment when the radius of the balloon is 20 centimeters, how fast is the radius decreasing? And here's the hint. This is a piece of information from algebra, geometry, you name it. You're supposed to know a sphere has a shape such as this one, and the volume is 4/3 pi r cubed. We should know that. So let's see what is given. It's losing air by this much, 8 cubic centimeters of air per minute, per minute. So that's dV dt, and since it's losing, it's negative 8 cubic centimeters per minute. How fast is the radius decreasing? We want dr dt. When r is 20 centimeters. So this is the translation of the whole thing, everybody. This is the translation of the whole thing. As long as we have that, practically we are done. So we want dv dt, dv dt. And to do so, if I take the derivative of this with respect to time, dv dt, 4/3 pi is a number, it remains. So 4/3 pi, and I'm going to just differentiate r cubed, which is 3 r squared dr dt. This 3 cancels out this 3, 4 pi r squared dr dt. I can solve for dr dt, or I can plug in. So if I plug in, I'm going to replace this with -8, and I'm going to replace the r with 20. And as you know, 20 squared is 400. Times 4 is 1600. So we are going to divide both sides by 1600 pi. -8, we have the negative sign here, divided by 1600 pi, that's dr dt. And 8 goes away, 1600 is 200. So minus 1/200 pi, units of the numerator, r over the units of denominator, time. So negative 1/200 pi centimeters per minute precisely. We change the pi using a calculator, 3.14159, and it continues indefinitely. And with a bunch of decimals, we get almost minus 0.001592 centimeters per minute. You want to pay attention to the number of decimals and how they ask you accordingly. We want to graph this function, f of x equals -x cubed plus x squared plus x. And the steps is, in addition to algebra and pre-calculus steps, find relative extrema by finding f prime, setting it equal to 0, doing a sign graph. Find inflection point by finding f double prime, setting it equal to 0, do a sign graph, and sketch the graph. So what I want to show you is reminding you of the pre-calculus stuff. First of all, I take the -x out because I want to factor this. I rather have this with a positive coefficient. It can't be factored, so I'm going to use the quadratic formula. So for this part, this class, when I set this equal to 0, this gives me 0. Again, I want to make sure we understand. I'm trying to find the intercepts. If I set this equal to 0, this gives me x equal to 0. This part, I am using the quadratic formula. This part, a is 1, b is -1, c is -1. and we get those. So minus b, minus -1 makes it +1, plus minus b squared minus 1 quantity squared minus 4 times a times c over 2a. And it becomes 1 plus minus square root of 5 over 2. In other words, the intercepts are located at 0, 0. This is 0. 1 plus square root of 5 over 2 and 1 minus square root of 5 over 2. Now, I can graph this using a pre-calculus stuff, okay? And because this is minus x cubed, the leading term, so this is called the end behavior, right? The graph looks like minus x cubed, so the second and the fourth quadrant. As far as the intercepts are concerned, so we have 0, 0 here. And then 1 plus square root of 5 is about divided by 2. This is about 1.62. So this is 1 and 2, so somewhere here. And this one is about 0.62, but negative. So here's -1, here's -2. So it's somewhere here. Again, this is not too scale. So, and each one has a multiplicity 1. I'm going to remember we talked about multiplicity because this has degree 3 and there are 3 answers. Each one has a multiplicity 1. When the multiplicity is odd, the graph crosses the x-intercept. When it's not, it doesn't. So therefore, the graph, okay, looks like this, has to come back up at some point, and it has to come back down at some point. We may not know where and when it comes back. We may not know intervals of increasing, decreasing. We may not know where it's concave up, concave down. So a lot of information we don't know, but here's a rough sketch from pre-calculus, and it works perfect. But we are going to add the calculus and make it more precise. So I'm going to clean up the mess. And I'm going to start with CP. So I'm going to differentiate this. And so differentiate this. This is easier. Minus 3x squared plus 2x plus 1. So I'm differentiating this. Because I want to set it equal to 0 and solve it, I'm going to take the negative sign out. So I get minus 3x squared minus 2x minus 1. And since I want, so this is 3. It's not a problem. So it's 1 and 3. Since I want two numbers, the product is -1. One of them is 1. One of them is -1. You got to make sure the middle term works. This is minus 3x. This is plus x. They add up to minus 2x. You set this one equal to 0. You get 1. You get this one equal to 0. You get -1/3. So there are two critical points. And to find extrema, local max and mean, we are going to do a sign graph. So here's x. Here's a number line from negative to positive infinity. At x equals -1/3. At x equals -1/3, f prime is 0. At x equals 1, f prime is 0. So we are going to pick up TPs, short for test points. So we write down here TP. And so in between this, of course, the easiest one would be 0. Here's -1, here's 1. And by the way, they are going to alternate. So if you put the 0 here, for example, this becomes minus, this becomes positive. The product of these two is negative. With this negative makes it positive, and they are going to alternate because we have two answers. It's of degree 2, we have two answers. However, you can plug in -1 if you want to continue with testing. This becomes -2. This becomes minus 3 plus 1 negative. Their product is positive, but this negative becomes negative. Same thing here. Now, let me throw in the arrows. Means it means decreasing from negative infinity to minus 1/3. Union 1 to infinity. And it's increasing from negative 1/3 to 1. That's the meaning of it. Then we have a local mean and a local max. Because it's changing from decreasing to increasing, we have a local mean here. You have to put it back into original function to find both coordinates. And because it's increasing and then decreasing at this point, we have a local max. We have to plug it into this to find it. So if you plug in 1 here, this becomes minus 1 plus 1 plus 1, and it becomes 1. That's easy to calculate. And so we have local max, plug in 1, we get 1 at 1 comma 1. For local mean, we have to plug in negative 1/3 into the function. So f of negative 1/3 means minus negative 1/3 cubed plus negative 1/3 squared minus 1/3. So negative 1/3 cubed is negative 1/27, with this becomes positive 1/27. This one is plus 1/9 minus 1/3, and 27 is a common denominator. So this is 3/27. This is 6/27. So they add up to negative 5 because this is minus, okay? My apologies, this is 9/27. Okay, 9/27. So minus 9/27. And so we have negative 5/27. Therefore, we are going to write local minimum is negative 5/27 at the pair negative 1/3 negative 5/27. And I have already mentioned where it's increasing, where it's decreasing. We just write it up. Increasing is where it's positive or arrow up in this vicinity. Decreasing otherwise, and we put it with the union to show that. The next part is to find f double prime and move on. So we are going to the next page, and I'm going to write everything we found from the previous page. Number 1, here's the function. Number 2, here's f prime. Number 3, here's the intercepts. And number 4, max, mean, and we are ready to go to f double prime, which means we are going to differentiate this, everybody. So we get minus 6x plus 2. We're going to set this equal to 0. And I hope you realize when you set this equal to 0, x becomes 1/3. And so we are going to do a sign graph using a number line. So here's a number line. We are going to put x here, f double prime here. We're going to go from negative infinity to infinity. Here's 0, and here's 1/3. At 1/3, f double prime is 0, everybody. Now, to the left of 1/3, the easiest point would be 0. So let's go with TP. We're going to pick 0 here. We're going to put 1 here. And if we put 0 into f double prime, it becomes positive 2. And if you put 1, becomes negative. So they alternate, obviously, which means it's positive here, concave up from negative infinity to 1/3, negative here, concave down from 1/3 to infinity, and 1/3 is the location of IP, the inflection point. You have to put it back into the original function and evaluate it. So let's do that. So it's concave up from negative infinity to 1/3, concave down from 1/3 to infinity, and let's evaluate. Negative 1/3 to the third is 1/27, so minus 1/27 plus 1/9 plus 1/3. 27 is the LCD. So this is -1. This becomes 3. This becomes 9. They add up to 12 minus 1, or 11 over 27. So the IP takes place at 1/3, 11 over 27. Now we are going to summarize the whole thing into this table, and we start graphing. X-intercept takes place at 0, 0. Another x-intercept at -0.62. Again, we are going to decimal representation for the sake of graph, so we can graph it. So -0.62 is between 0 and -1, so closer to -1, so somewhere here. And then 1.620 between 1 and 2, so somewhere here. So we have those three x-intercepts, and all of them, we know the graph crosses those. The next one is a maximum at 1, 1. And we're going to put an arrow. Anytime you have a max and min, you put a double arrow, meaning it can't cross it. The IP is at 0.33 and 0.41, so somewhere here. The minimum at -1/3 minus 5 over 27. We use this because it makes it easier to see that. So -0.3 somewhere here, -0.2 somewhere here. So puts it somewhere here with a double arrow. Now we know -x³. I've already discussed the end behavior, the second and fourth quadrant. So it comes down here, goes like that. Here's the graph. Notice the function is concave up all the way to here, from -infinity to here, the inflection point, and it's concave down otherwise. It's decreasing here, increasing here, decreasing. So everything that we have discussed, it's shown here.